Hello, welcome to another module in this massive open online course on estimation or estimation theory for wireless communications. And in the previous module, we have started looking at a basic model for estimation. We have considered a sensor network and a noisy observation model for the sensor network, in which our observation, remember we have our observation y, which is equal to the parameter h plus the noise. So, this is your observation at the center, which is equal to the parameter that is denoted by h plus the noise that is denoted by v. And in addition, we have seen then when this v is Gaussian with mean 0 variance sigma square, then this y is also Gaussian with mean given by the unknown parameter h and variance sigma square. Therefore, the probability density function of this observation f y of y, that is the PDF of this observation y, that is the random variable y, is 1 over 2 pi square root sigma square e raised to minus 1 over 2 sigma square y minus h square. This is the probability density function of the observation y at the sensor node corresponding to the parameter h and Gaussian noise v with mean 0 and variance or power sigma square. So, this is what we have seen in the previous module. Now, let us extend this module further. Let us extend this to a scenario where a sensor node is making multiple measurements in time. So, now I would like to consider our sensor node scenario. So, let us go back to our sensor network, our sensor node, which is now making multiple measurements. So, our sensor node which is making multiple, so our sensor node is making, again remember, measurement, but this time it is making multiple measurements of this parameter h in time. So, we have measurements y1, y2, yn, and these are the multiple measurements being made at different time instants 1, 2 up to n. So, we have the measurements y1, y2, yn, capital N measurements being made at capital N time instants. And interestingly, now you can also consider this as a sensor network with multiple sensor nodes, with capital N sensor nodes making capital N measurements, right. Instead of considering these as single sensor making n measurements in time, one can also consider this as n sensors making multiple measurements at a single instant of time. So, this basically captures both the single sensor and also a multiple sensor scenario for the measurement and subsequent estimation of the parameter h. Now, therefore, these measurements can be modeled as each measurement is basically a noisy observation y1 equals h plus v1, y2 equals the parameter h plus v2, so on and so forth, yn, the nth measurement is the parameter h plus Vn, and similarly we also assume that all these noise elements V1, V2, Vn are noise with 0 mean and variance sigma square. So, each measurement Yk at the kth instant of time is h plus Vk, where k can range from 1 to n, we have n instants of time. So, in general I can represent this as the kth measurement Yk equals h plus Vk, where k denotes the kth instant of time, and naturally the probability density function corresponding to Yk is f of yk of your observation yk is again the same. It is a Gaussian with mean given by the parameter h and variance sigma square. So, this is given by this probability density function, which is 1 over square root of 2 pi sigma square e raised to minus 1 over 2 sigma square yk minus h whole square. This is the probability density function. This is the PDF of each individual observation y of k. This is the PDF of each individual observation y of k. We are saying the same thing, that is each individual observation made by the sensor at time instant k is a Gaussian, has a Gaussian probability density function with mean given by the unknown parameter h and variance given by the variance of the noise Vk, which is sigma square. Now, what we are interested is we want to come up with the joint density of the probability of the observations y1, y2 up to yn. We want to come up with the joint PDF or the joint probability density function of the observations y1, y2 up to yn, which is represented by f subscript y1, y2, yn of y1, y2 up to yn. We want to come up with the joint probability density function. This is the joint PDF of these observations y1, y2 up to yn. And towards this end, we will make a simplifying assumption to come up with the joint probability density function. We are going to assume initially that these noise elements V1, V2, Vn are IID, that is, these are independent, identically distributed. So, the noise elements, so the assumption that we are going to make is towards this end to develop the joint probability density function, the noise elements or the noise samples V1, V2, Vn are IID. What do we mean by IID? That is, they are independent and identically identically distributed. That is, all of these are identically distributed. That is what we already assumed, that is, they are Gaussian with mean 0, variance sigma square, and also they are independent, right. These noise samples V1, V2, Vn are independent, which means the observations y1, y2, yn are also independent. So, the observations y1, y2, yn, since the noise samples v1, v2, vn are independent, the observations y1, y2, yn are independent, and therefore, what we have, so since v1, v2 noise samples v1, v2 up to vn are independent, this implies that basically your observations y1, y2 up to yn are also independent. In fact, they are independent, identically distributed with mean h and variance sigma square. Therefore, the joint probability density function of the observation is of the observations y1, y2, yn is the product of the individual probability density functions corresponding to the observations, because the observations are independent, and that gives us an important result, that is the joint probability density function which we were talking about before, f of y1 y2 up to yn of y1 comma y2 up to yn. This is equal to the product of the individual probability density functions, that is f of y1 times f of y2 times f of yn, that is, this is the product of the individual probability density functions product of the individual probability density functions of the observations, and we know what is the individual probability density function of each observation, that is 1 over 2 pi sigma square root of 2 pi sigma square e raised to minus 1 over 2 sigma square times y1 minus h whole square times the product 1 over square root 2 pi sigma square e raised to minus 1 over 2 sigma square y2 minus h square times 1 over square root of 2 pi sigma square e raised to minus 1 over 2 sigma square yn minus h whole square. This is the product of the individual probability density functions corresponding to the observations y1, y2 up to yn. And now, simplifying this product of the individual probability density functions, you can clearly see that this is given as 1 over, that is collecting 1 over the square root of 2 pi sigma square terms. I have 1 over 2 pi sigma square raised to the power of n by 2 e raised to minus 1 over 2 sigma square summation, all the terms in the exponent will add up, k equals 1 to n, summation k equals 1 to n yk minus h whole square, and this is your joint probability density function. This is the joint PDF of the observations y1, y2 up to yn. And now, I would like to bring to your attention an important point. Note that while deriving this joint PDF, we have ignored the fact so far that this parameter h is an unknown parameter. This is the parameter that we are trying to estimate at the sensor node or the fusion center. This parameter h, as I pointed out to you also in the previous module, that this parameter h is unknown. So, realize that in our probability density function, this parameter h is, this is unknown. This parameter h is unknown, and therefore, one has to estimate this parameter h this is known as parameter estimation. This is what I pointed out to you in the previous module, that is estimating this parameter h, that is finding out what this parameter, computing the value of this parameter h is termed as parameter estimation. And this probability, joint probability density function as a function of the unknown parameter h, because there is a parameter which is unknown, as a function of the unknown parameter h, this is known as a likelihood function. And this is the important point, and one of the central points I would like to point out in the entire framework of estimation theory, that is this probability density function viewed as a function of the unknown parameter h is termed as the likelihood function, that is the joint probability density function of the observations. Let me put it this way: the joint PDF of your observations y1, y1, y2 up to yn as a function of the unknown, as a function of the unknown parameter h is termed as a likelihood function. This is the likelihood function corresponding to the, this is the likelihood function which is basically the joint probability density function of the observations y1, y2, yn, which is viewed as a function of this unknown parameter h. This is known as the likelihood function of the parameter h. The argument is the unknown parameter h. In a certain sense, this represents, for each value of h, this represents the likelihood corresponding to the unknown parameter h, right. And we would like to use this likelihood function to find the estimate of the parameter h, and therefore one natural framework to find an estimate of the parameter h is to find that value of h for which the likelihood is maximum, and that is known as the maximum likelihood estimate. And this is an important aspect of estimation, or this is an important concept in estimation. We have derived the likelihood function of the unknown parameter h. Now we would like to maximize this likelihood function and find out that value of h which maximizes this likelihood function, and that is known as the maximum likelihood estimate. So what we would like to do is, first let us look at this likelihood function, right. What is this likelihood function? This likelihood function is your joint PDF, that is f of y1, y2 up to yn, y1, y2 up to yn, which is equal to 1 over square root of 2 pi sigma square e raised to minus 1 over 2 sigma square. In fact, this is 1 over 2 pi sigma square raised to the power of n by 2 e raised to minus 1 over 2 sigma square, k equals 1 to n yk minus h whole square. This is a function of the unknown parameter h. Now what I am going to do, I am going to define this as the likelihood of the observations y bar parameterized by h, where y bar is the observation vector, y bar is the observation vector. Remember, we have multiple observations. So y bar is the observation vector y1, y2 up to yn. So this is basically my observation vector. This is contains all the observations. This y bar is my observation vector, and P of y bar h denotes this is the likelihood. What is this? This is the likelihood function of the observation vector, and this is parameterized by h denotes, this is parameterized by h. The terminology that is used is P, that is we have this observation vector y bar which is of length n, which contains observations y1, y2 up to yn, and P of y bar semicolon h. Remember, it is not a comma, it is a semicolon h, which denotes or which signifies the likelihood function of the observation vector y bar parameterized by this unknown parameter h, that is P of y bar h. Yeah, so this is the likelihood function of the observation vector y bar, which is parameterized by h. And now let us look at this thing, this likelihood function. We have derived the expression for this likelihood function. Now, as we said, this basically this is the likelihood function which corresponds to the likelihood of the observation vector parameterized by h. And now what we would like to do is we would like to maximize this likelihood function P of y bar h. This is your likelihood function. What we would like to do is we would like to maximize this likelihood function to find the estimate which is termed as the maximum likelihood estimate. In short, this is also denoted by ML. So, we would like to maximize the likelihood function to find the maximum likelihood estimate of the unknown parameter h. This maximum likelihood, this concept of maximum likelihood is also abbreviated as ML, which denotes the maximum likelihood. Now, let us look at this. Instead of maximizing P of y bar parameterized by h, I can also maximize, that is maximizing this is equivalent to maximizing the log of P of y bar parameterized by h. Because the function is maximum, the logarithm is also maximum, because log is a monotonically increasing function. We are talking about the natural logarithm. Let me denote this by ln, that is log to the base e. When a function is maximum, its logarithm is also maximum, right. So, if function is maximized, instead of maximizing a function, finding the point h where the function is maximum, it is convenient in this problem, since we have an exponential, we would like to find the parameter h for which the logarithm of the function is maximum. Now, let us look at the logarithm of the joint density function. The logarithm of the likelihood function is basically your logarithm of 1 over 2 pi sigma square raised to the power of n over 2 e raised to minus 1 over 2 sigma square summation k equal to 1 to n y k minus h whole square. And if I take the logarithm of this likelihood function, now I can get, you can see, minus n over 2 ln 2 pi sigma square minus 1 over 2 sigma square summation k equals 1 to n of y k minus h whole square, and this is basically the log of the likelihood, which is denoted by script L y bar parameterized by h. This is basically your log or the natural logarithm ln of P likelihood function P of observation vector y bar parameterized by h. This is also termed as the log likelihood function, the logarithm of the likelihood function. This is also termed as the log, this is also termed as the log likelihood. Instead of maximizing the likelihood, I can maximize the log likelihood of the observation vector y bar. And now you can observe something interesting. Look at this part in the log likelihood, this is a constant. So basically this is always a constant, so I need not worry about this, I need not worry about maximizing this, right. If the function is maximum, the function plus a constant is also a maximum. So I need to maximize this part, but this part has a negative sign, so I need to minimize this part. So I need to look at where I am, which part I am. This function has a negative sign, so to maximize the log likelihood function, I need to minimize this part. That is, in order to maximize minus 1 over 2 sigma square summation k equal to 1 to n yk minus h square, if I remove the negative sign, I can minimize the rest of the argument. And now observe that this factor 1 over 2 sigma square is a constant, so all I am left with is minimizing this component, which is summation k equal to 1 to n yk minus h square. So what I am saying is that is equivalent, this, although this log likelihood function might seem complicated to begin with, it is equivalent to basically minimizing this part, that is minimize this part. And now that minimization is easy, I can simply differentiate this and set this equal to 0 to minimize summation k equal to 1 to n yk minus h square. To minimize this, differentiate and set equal to differentiate and set equal to 0. And if I differentiate this, what am I going to get? If I differentiate this with respect to h, I am going to get summation k equal to 1 to n twice yk minus h equal to 0. That is, differentiating and setting equal to 0 implies summation k equal to 1 to n twice yk minus h equal to 0, which basically implies that summation k equal to 1 to n of yk equals n times h, which basically implies that this occurs at your h hat equals, what is the value of h that occurs, this occurs at value of h equals, this occurs at value of h, which is equal to 1 over n summation k equal to 1 to n y of k, and this particular value of h is denoted by h hat. This is an estimate of the unknown parameter h, that is the value of h at which the likelihood function is maximized is basically the estimate of the unknown parameter h. This is denoted by h hat, this is the maximum likelihood estimate of h. So this is your h hat which we have calculated, this is the maximum likelihood of estimate, this is your maximum likelihood estimate. Let me write this clearly, this is the maximum likelihood or ML this is the maximum likelihood or ML estimate of h, and one can also denote this by subscript ML to denote that this is the maximum likelihood estimate. Yeah. So this h hat is the maximum likelihood estimate, and look at this, this is simply the average of the observations. What is this? This is the average, simple average or arithmetic mean of observations, your observations y1, y2 up to yn, and this is also known as, this average is also known as the sample mean. That is, the maximum likelihood estimate is given by the sample mean. What is the sample? We have a sample of observations y1, y2, yn, and the mean of this sample is 1 over n summation k equal to 1 to capital N yk. This is the arithmetic mean or the sample mean of the observations, and this is very intuitive. What we are saying is the maximum likelihood estimate, the maximum likelihood estimate of the unknown parameter h is simply to take the average of the observations at the sensor node, which is something very intuitive, but we have derived this analytically rigorously and justified this. That is, we have formed the likelihood function, and this value of h, this sample mean of the observations, maximizes the likelihood function. Therefore, this is known as the maximum likelihood estimate. So, this sample per, so turns out that in this case the sample mean is basically your ML, the sample mean is your ML estimate, which is something that is very important, which we have learnt in this module. So, what have we started with in this module? We have extended our single observation model to a multiple observation or an observation vector model. We found out the joint probability density function of these observations, and as a function of the unknown parameter h, we said this is termed as the likelihood. The value of h which at which this likelihood is maximum, which corresponds to the maximum likelihood of the parameter h, is known as the maximum likelihood estimate, and for this particular problem we have derived the maximum likelihood estimate as h hat equals 1 over n summation k equal to 1 to n yk, which is the sample mean. And this is a very interesting aspect. This is the maximum likelihood estimate, which is a very interesting and very important and a very powerful estimation paradigm. This is the maximum likelihood estimation. This example of sensor node making multiple measurements illustrates the basics of this maximum likelihood estimation principle, and in the next module and in further modules we will explore this maximum likelihood estimate further and discover other properties of this maximum likelihood estimation procedure and the maximum likelihood estimate that we have found. So, let us stop here and we will continue in the subsequent module. Thank you very much.